So we've done a bunch of examples. So let's kind of dive into, I'm going to go ahead and give you the fundamental theorem of Galois theory. So I'm going to give you the theorem here, and then we're going to spend, I'm going to give you the theorem here, and then we're going to spend a lot of time proving, building it up. So theorem. Fundamental theorem. Galois. So let's let K and F be finite in Galois. I want this to be a Galois. So remember what that means is if you look at all the automorphisms of F and fixed K is actually the fixed field of this. Right? Or the way I like to say it is if you have any element of F that's not in K, then there's some automorphism of F that moves it. And there is a one-to-one correspondence between the set of intermediate fields and subgroups. Then there exists a one-to-one correspondence between set of intermediate fields of extension K inside F and the set of subgroups of Galois. So, given a subgroup of the Galois group that corresponds to an intermediate field and vice versa. And I will tell you how it's given. Suppose we have an intermediate field. Now E prime, if you remember, so input field, output subgroup of the Galois group. And this is everything in the Galois group that fixes E, right? Okay with that? So this is actually the Galois group of that. So that's what E prime is, because this is the set of automorphism of F that fix E. Okay. Such that the following hold. A if you have two intermediate fields L and M, then that is the degree of the extension of M over L is equal to the index of M prime inside of L prime, right? So this is, of course, the vector space dimension of M over L, and this is the index of the subgroup M prime and L prime. These are identical. So in particular, you order the Galois group. So the order of the Galois group is actually equal to the degree of the extension F over K. So, for example, if you have a Galois extension of Q of order 5, then, you know that the Galois group is of order 5, and so it has to be 6 of order 5, right? And there are Galois extensions for 5 over, they're hard to find, they're there. Number B, if F is Galois over the intermediate field E, right? The F is Galois. But it's not necessarily true that E is Galois over base field. And E Galois over K, if and only E prime is normal in the Galois. And in this case, that is normal. What do we know about normal subgroups? You can mod out by it. In this case, the Galois group of F over K modulo this normal subgroup. Anybody want to guess at this? So when you have this, when E intermediate in the Galois group of E over K is isomorphic to Galois group of F over K, Galois group. So here's kind of a picture. So for fields, this gives so let me draw it this way. So you've got this tower of fields. And the correspondence gives you but the correspondence sort of works in the right. So if this is F, then what is F prime? It's everything in the Galois group that fixes F prime. This is the small field K. What is K prime? It's everything that fixes all the automorphisms. So this is all the Galois group. Right. And this is containment goes the other way. It's, and if you look back at that diagram that we did last time, field Q adjoint omega alpha, where alpha is Q2, you can see this correspondence. So a good exercise is for you to look at this theorem and take that picture and show you, convince yourself that this all works. So here's the big thing about the Galois theory. This prime operation is a one-to-one correspondence between intermediate fields and subgroups of the Galois group. And we've got a few things going on. The indices are the same, and we saw that in that example last time. And F happens to be Galois over every intermediate extension. But E is Galois over K if and only if it's a normal subgroup. And in this case, the Galois group, B over K, is equal to this function. So that is the statement. I think that our pictures have sort of, you see that something like this is going on. So now what we got to do is get our hands dirty and start proving this is true. So let me start with a lemma. Oh, any questions for you? Get rolling on the heavy lifting. Yes.
So we're going to show that like the double prime axis, like X is the identity. Like,
Most examples that you will come up with, that is the case. The double prime is in the situation that we have here, that in general, in the most general case, a double prime doesn't act like the identity. And we call an intermediate either field or group closed if the double prime is the identity. So if you start with a field, you prime it and you prime it back. If you get back to where you were, we say that that field is closed, and the same with the group. In this case, we're going to discover that the intermediate fields and the intermediate groups are all closed. So let K and F be Galois. Let K and F be Galois with intermediate fields L and M. And with L, M, intermediate, maybe not common. Also let G be the Galois group of F over K and H and N be subgroups of G. Random subgroups, following conditions hold. Number one, A. Prime is 1 and K prime is G. I'm gonna leave some of these correct, so I'm just gonna follow my way with that one. Number B, 1 prime equals F. B. If L is an M, then M prime is an L. Prime, say. D, H is N. But N prime is contained. Number E, L is contained and H is contained in H double prime. And F So the prime is equal. So in other words, you could be defective here, right? You might have, so what this is saying here is when you start with a field and you double prime it, it gets bigger. Right? And maybe strictly bigger, maybe. When you double prime a group, it gets bigger, maybe strictly bigger. But by the time you hit the prime level, this defect is cured, right? When you take L prime and you double prime that, you fall, and you take H prime and double prime that. Right? So, gonna talk our way through some of it again. Okay, so yes,
Sorry, I don't think this is related, but this reminds me of something from that we learned in the math course in the fall, which was about the maximal ascents and descents. Something like you take a maximal ascent, it's so that if you take the descent, the next ascent will take you back. I don't know. Is this anything related?
you see these kind of things, like in places like topology analysis as well, where you get these sort of pseudo closure operations, right? And, this kind of thing comes up quite a bit. When you have these
One
kind of
question.
correspondence.
One
Yeah,
question.
I've seen theorems in topology and analysis. You have almost an identical statement right here, but you're doing different objects. Okay, so F is the
Jim.
big field. F prime, this is the set of automorphisms that fix all of F prime. Well, I know what that is, right? The only automorphism that fix everything in F has to be the identity.
Jim,
And what is K prime? This is the set of all automorphisms that fix K prime, and that's all of G by definition, right? Because G is the automorphism that fix K. B, 1 prime equals F. So what does this mean? This is everything in the field is fixed by the identity. Once again, that has to be everything. Right? Because the identity fixes everything.
one
Let's
question.
look at
One question.
C. So let's let
One question.
so we've got that L is contained in M. I want to show that this is contained in L prime. Well, what does it mean for sigma to be in M prime? Then sigma of M is equal to M for all M and N. Right. That's what it means for sigma to be in M prime. It means it fixes everything in the field M, but M contains L. So sigma L is equal to L for all L and L. Therefore, right, so really this is just chasing definitions, right? E. All that precious parts of my anatomy is very similar, right? Suppose that N is in N prime. So, this means, of course, that N is an element of the field, right? And this field is determined by what is N prime. This is the set of alpha and F such that, sigma alpha is equal to alpha for all sigma in it. Right. So let's suppose that we have this N and N prime. So that means that sigma fixes N for every sigma in N. But in prime, I should say. blunder. Sigma n is n for all sigma in, n. But n contains, doesn't it, h. Therefore, for all sigma in h, sigma n is n. Therefore, n is in h prime. So, got that? Everybody okay? How about number E? We need to show that L is contained in L double prime. So it helps my pea-sized brain to write this down a little bit, kind of keep track of things. For E, we want to show that first that L is in L prime. So let's write this down. No. What is L prime? Well, that's supposed to be a group, and it is the collection of everything that fixes L. That's what L prime is. And L double prime this is back to the field. This is everything in F is fixed by everything in L prime. Right. So suppose what if L is an L? Then sigma L is equal to L, right? For all sigma and L prime. Right? Therefore, L is contained in L double prime. Everybody agree? We do the same thing. It's similar to just chasing the definitions, write down what it means to, write down what H prime is and what it means to be an H double prime. Right, okay, so far. Okay, so that takes care of E. F is the most fun. What about F? Well, notice that L is contained in L double prime, right? And so, let's see which one I want to apply here. L is a field, right? So by this one, we reverse the containment here. That is to say that L double prime is contained in L prime. So okay. what about the other containment? So L triple prime is bigger than L prime, that's not too bad. What about the other containment?
We can use E.
I'm sorry?
Again, using E,
Okay, so how are you gonna use it?
L prime is less than or equal L triple prime.
Okay. Right? And so now what? Right. But, well, right. Let me clear this. So we've got this already. Right? So we've got the L prime is sort of the big one here. So now I've got the other containment as well. And the other one is similar. In fact, it's pretty much the exact same body. Okay, any questions on
Yeah, I have one
No.
question.
that? So it's probably worth sort of noting here. Note that, right. That is Galois over K. Because notice that, of course, we always have this containment. All right, that containment is always good. So what we need is the other containment. Well, what is K prime? It's all the automorphisms of F that fix K, so it's everything. So when you're at the K prime level, this is the entire Galois group. And so what does this mean? This is the fixed field of G, which this is equal to K if and only if F is Galois. Right, because that's exactly what it means to be Galois, is the fixed field has to be, right, and no more. More generally, well, we'll up this observation here. If you have then F is Galois over E if and only if. Same sort of argument before. So now, if you remember back to our statement of the fundamental theorem of Galois theory, I'm using that as kind of a spoiler. I remember somewhere I said that F actually is Galois over any extension. So this comes full circle on what you were saying earlier. This must mean that every intermediate field is closed if you believe what I wrote down first, right? And notice this always holds. So kind of a cool thing is if you have a Galois extension, finite Galois extension, F over K, if that extension is Galois in the first place, then that means the K is equal to K double prime. That means that that'll hold again for every intermediate extension, right? So really all you need is Galois over Bayes field, and it takes care of everything else for you. So here's a kind of a definition that I was kind of teasing about a little earlier. So it is very important when either an intermediate field or an intermediate group, when you double prime it and you get back to itself. And we've got a name for that.
If I want to prove that this is Galois over K, do I have to check both equations there or only one?
Well, so what's always going to happen is you only have to check one, because it's always true that K is contained. So if this is contained in here, which is equivalent to saying that the fixed field can't be too big, right? It's got to be this K. So definition. Let's suppose that you know, X is a subgroup K, or X is an intermediate extension so we're letting X be sort of variable, but neither represent a group. It's something the Galois group or intermediate extension. Then we say X is closed if X is equal to double prime. Of course, X is always contained in its double prime. And we say it's closed if you get equality here. Notice that let me make an observation. So in a certain sense, I'm going to claim that we're almost done with a big part of this. Previous one shows that we already have a one-to-one correspondence between closed and closed subgroups of T given by E goes E prime. So take a look at that lemma and you can see actually that what we have so far is a one-to-one correspondence between closed intermediate fields and closed subgroups of the Galois group. So our strategy right, because So if E goes to E prime, and then you compose it further. Right. Then that composition gives you, and of course, notice that this is closed, right? Because this is equal to E prime, prime, prime. So if E is closed, its prime is closed. And when you get, since E is closed, you get back here. And if you have an intermediate subgroup, so the field here is closed because it equals its double prime. And so E corresponds to a closed subgroup. This composition is the identity. H corresponds to a closed subfield. This composition is the identity. So what we've already got is we've already got a big chunk of Galois. We have this correspondence between closures. But of course, at this point, we have to entertain the possibility that some of the subgroups aren't closed, some of the subfields aren't closed. That could be a hazard for us. And so the strategy now is so that if F is algebraic in Galois, right? One, if F is algebraic in Galois, then all intermediate fields are closed. So I'm going to need at least algebraic and Galois, which, I mean, this is Galois theory, so Galois doesn't seem like too bad of an assumption now, does it? And algebraic, and since we're studying algebraic extensions, that would be good too. This will get me that all intermediate algebraic Galois. Notice I didn't say subgroups. If F is finite dimensional, then all subgroups. All subgroups of Galois. Yeah. Okay. Notice this one's a little bit more restrictive. To get the groups closed, we're going to invoke finite dimensional. Notice this is a little bit more loosey goosey because I'm assuming Galois both times. Algebraic, I could be infinite dimensional. And in fact, I can give you many examples of extensions, Galois groups. Finite dimensional is tighter. When I say finite dimensional, I don't have to say algebraic. Any finite extensions algebraic. All right. Okay. So, any questions? Okay, so we've got the business about closed. So basically, what I'm motivated now is I'm trying to say, okay, when can I show that my intermediate fields or my intermediate groups are closed? So let's start with this lemma. But K, inside L, inside M, inside F, these fields. If the degree of M over L is finite, then you get inequality. The index of P prime and N prime is less than or equal to this. Well, I guess it wasn't. So we get that anyway, well, we just wouldn't be as useful. In particular, if the degree of F over K is finite. Yeah. The order, the Galois group of F over K is less than or equal to.
Is there a particular reason for not using two fields instead of four?
Well, because I want this to apply to any pair of intermediates, right, as opposed to, I don't wanna have to assume it's either the top or the bottom. Right.
You're still thinking about these in terms of, okay, are these in terms of K vector spaces or L?
Okay, yeah. Yes, the degree of this extension is, the degree of this extension is the dimension of M over, L as an L vector space. Okay, other questions? So let's do this. We're going to proceed by induction. We'll proceed by induction. On the degree of M over L. What happens in the case where N equals 1? Well, in the case of N equals 1, since there's a containment here, that means that M and L are the same field, right? And this is, in this case, we have certainly that L prime, the index of M prime and L prime, because what is M prime? This is everything that fixes M. What is L prime? It's everything that fixes L. These have to be the same thing. This is 1, this is 5. So we've got the base case done. So we'll assume that N is bigger than 1. Now suppose N is bigger than 1 and assume conclusion for all integers I strictly less than N. Right, so we'll do the strong induction there. So the first thing I want to do is I want to reduce this to a simple case. In what sense? I'm going to select a U and M, but not an L. And of course, I can do this because I'm assuming that n is bigger than 1. So this makes it 1. And U is algebraic over L. And how do I know that?
Because the tension is finite.
Right, so U is algebraic. Well, right, because that's a finite extension. And let's suppose that it has irreducible polynomial F. F of X and Lx is minimal polynomial for U of degree, let's say K is bigger than 1. Has to be bigger than 1 because I'm assuming that U is not in the field L. So if you look at the degree of LU over L, this is precisely equal to K, and M well, this has to be an open here. Right, because when you multiply this by this, you have to get in, right? Now, first, I'm going to suppose, well, let me point out if I will be also point out this has the consequence that okay, by the way, I'm assuming that what happens if K and N are the same thing? Right, so I said, so I want to kind of figure out what happens in the case of K is strictly less than N. What happens with K and N in the setup that we've had? What happens if K and N are the same integer? That's exactly right. M is equal to LU. So that sticking that U on the L is enough to get all of M, right? However, if K is less than this, then we apply induction. This is L. Which is, this is less than or equal to K, N over K. K, which is equal to M. And so we're done by induction. If K is less than N. Case K equals N. Next. So I'm going to pick it up where we left off here. we've got this licked, as long as this LU is smaller than M. What if LU equals M? We gotta do something a little bit different, and we'll get that figured out next time. Okay, any questions on this? All right. Well, Pedro, you okay out there? Any questions?
Yeah, I have
All
one
right,
question.
well, we will see you all on.
Hmm.
Say a weekday, man,
I have
Friday.
one- I have one question.